Hi, everybody. So yeah, I'm going to demonstrate an application for the iPad and also, as of last week, for M1 Macs that is also an electronic book. It's essentially an application that draws a lot of space-filling curve pictures that is surrounded by a nicely typeset book. The application has its own tech interpreter in it, and so it shows, high-quality math equations when you need it. But all of the illustrations in this application are basically C subroutines. They animate. You've got lots of controls to play with things. You've got the ability to do resolution-independent zooming because the subject of this book is space-filling curves, which really want to be zoomed into very far. So we all know about the Hilbert curve, and we can create approximations and so forth, but this allows you to look at the mapping from the unit interval to the unit square. You can see where the triple points are at, say, 1/6 and 1/5 and 1/2 and 5/6. And you can have fun with an infinite zoom, for instance, and the frames are being computed as, there's no movie in this, just like there's no PDF in it, and you can look at it as a sort of a visual shepherd tones animation. Well, how do you generalize the Hilbert curve? Well, you increase the subdivision order of the grid to, in this case, 6 by 6, and you can find Hamiltonian paths from the lower left to the lower right, and they will all create space-filling curves, and you can fill them in, show them as polygons, see what the grids are, and so forth. And so you can zoom in and see what the patterns are there. And so that's the first way you generalize. But another way you can generalize is you take those grids and you start perturbing the edges of the four edges of the subdivision. And that leads to fractal tiles, which also have a mapping from the unit interval to every point in the fractal tile. And again, you can zoom in arbitrarily far and see what the structure of things are. And that leads to another idea, which is infinite sequences of these motifs that are rotationally symmetric. And so you can really have some fun and create some marvelous designs. And that is actually the prototile for a space-filling curve that is a fractal tile. And we'll compute it, and there's your fractal tile. It's filled in. It's a polygon with 71 million line segments in it. And then you've got enough combinatoric space to really have fun and play in it. So these are just some fanciful designs I came up with. Every one is a space-filling curve that creates a fractal tile that tiles the plane. And you can have fun with textures or different ideas. This one is particularly weird and interesting. If you zoom in, you'll see it has different structures and different parts of it. Well, it turns out that rotational symmetry is not necessary. You don't have to do the same thing on the top of the subdivision as you do on the other three sides. So you can do nothing on the top of the subdivision, and suddenly you're getting tiles that have infinitely detailed boundaries, but the boundary is almost everywhere linear. So there's this world that lives between my old boss Mandelbrot's fractals and he was saying, well, there's linear and there's fractal, but it turns out there's an interesting world of form that's in between the two, because the boundary of this is infinitely long, has an infinite number of cell-similar details, but it is, in a measure-theoretic sense, almost everywhere linear. And so that leads us to half-domino curves, which is the opposite. You leave three sides of the square the same, and you perturb the top of the subdivision. And it turns out that this is combinatorially freer than the other situation, and you can find solutions on lower order grids. So here's our usual Hilbert curve, and the Hilbert curve is a degenerate half-domino curve. Why? Because two Hilbert curves cover a 1x2 rectangle. Well, guess what? You can take that pattern and you can find you can rearrange the subsquares in a 4x8 domino, and you can find other patterns, and every one of these generates a space-filling curve as well. So they're self-negative because they have unit area, infinite boundaries, almost every linear boundaries, and they cover exactly half of a domino. Well, so what I did then was I enumerated on the 12 by 24 domino, I enumerated 70,000 motifs that have the property that they are sort of, that the motif hews to itself and creates a tendril. And so, but again, they're self-negative, so two of them will cover a domino, so each one is a half domino, and they all create space-filling curves with crazy interesting borders that you can zoom in, and all of the infinite detail grows only on the horizontal boundaries of this tile. So I picked out some of my favorite ones, and again, you can zoom in and you can see that these 2 points are slowly converging. In the limit, they will be at the same point, which means that this fractal tile will be a gasket, and it will tile with itself. It'll tile a square. Four of them will tile a square. And I went through, and so then there's this one, for instance. Look at this. This is just lovely. This looks like something straight off of a Navajo rug. And so these self-negative designs, of course, show up throughout history in craftsmen and pottery and rugs and so forth. I like this one. It's sort of a Moroccan flavor. I like this one, which is a Greek key design. And again, the Greek key design details are only growing on the horizontal edges. So finally, this is the basis of a space-filling curve that you can apply to itself, and you can see what the mapping is from the unit interval. It spirals around, and it's a self-negative tile that tiles the plane. So those are half-domino curves, and they're an interesting world. And the app is called Hilbert Curves. It's available for iPad, iPhone. It needs a lot of screen real estate, and as of last week, it's available for $8 for M1 CPU Max. And finally, I just published a paper for an entire other world of Hilbert-style curves that shows that the Fibonacci numbers govern the boundary conditions for every single possible motif. So if you're interested in that, please just Google Fibonacci zippers and you will get to the paper. That's my talk.